same time, it could result in interesting cost savings over time. Now, you can also decide on what you think is the best bid price when you're doing this initially based on what's called the spot price history. So there is a history of the last 90 days availability, and you'll see this in the AWS console, or technically you can also get to it if you're programmatically accessing the EC2 APIs. When we make a bid for an EC2 spot instance, it can include things like the start time, the stop time, so when we want to use that virtual machine instance, and we could also configure things like persistence. So there is no specified stop time. We'll take our chances, run it as long as we can, with the understanding that it could be interrupted. So we're here now in the EC2 management console, where on the left, I've already clicked under the instances category on the spot requests view. This is where we get our spot request instances. Currently, we don't have any. However, I could click request spot instances. Now, when I do that, that'll open up a new page where we can determine what we want in terms of a one-time spot instance request, or do we want to request a fleet of spot instances? Because maybe we need that to support whatever workload it is that we plan on running at a discount, or for a specific duration. So for example, I want to use a spot instance with no interruption for 1 to 6 hours, which is called a spot block. So there are variations on how we do this depending on our appetite for risk and how much we want to save and the type of workload we think we're going to use. So I can set the target capacity that I want to bid on here. I can specify the AMI, the Amazon machine image, whether it's Linux, Unix, or Windows based. And I can search for specific AMIs if I really wish. I can take a look at the instance type, which determines the underlying horsepower. So I could go ahead and do that. I could click the select button over on the right and choose whatever it is of unused capacity that I want to try to get at a discount. All right, so I choose whatever I think I need to support my IT workloads based on that. So I'll just choose an item here and click select. And then I've got my allocation strategy where I can be focused on the lowest price, or I can have more of a balanced approach across price and availability zones and instance types. So again, it really depends on my appetite for risk, how important cost savings are balanced against the importance of the workload that's going to be running within those instances. I can also select the VPC where I want this deployed. So for example, maybe I'll choose VPC East. And I can also specify a zone and subnet down below. So I'll just choose one from the list. Notice I've also got links over here to create new VPCs and subnets if I didn't think to do that ahead of time. Then I can determine the maximum price. So I can use automated billing or a bidding, but I can also set a max price per instance per hour. Now remember, this is per instance. Up above, you might have requested more than one. So bear that in mind. Now, I could also click on pricing history. And here I can see within the availability zone the pricing history, and I can see the current date and time. Now I can change some of these metrics up at the top, like Linux and Unix. I can choose the instance type. I can choose the duration. And I get an idea here. I can look at the graph here. I can also see the availability zone in the legend is the different colors on the graph of what the pricing looks like it would be. So I notice here in US East 1D as an availability zone, as well as US East 1F, it appears that the pricing is a little bit more than it would be in some of the other availability zones. So this can help me make my choice when I want to work with an EC2 spot instance bid. So at this point, I could continue on and click Next. Then I get to specify some more details about the storage. I can set monitoring options. I can configure metadata tagging if I so want to. And of course, we all know that when we work with EC2 instances, we need a public and private key pair to authenticate to them. So we've got those options along with our security group, firewall rules, and essentially the normal settings that you would encounter when deploying a standard on-demand EC2 instance, with just a few little changes. One when we're aligning AWS service offerings with business requirements, there are times we'll be stepping into the development realm. And that's what we'll do here as we talk about the Amazon Web Services Simple Queue Service, or SQS feature. At the development level, a queue is a temporary storage location. Now, for what? Well, it would be the resultant output from an application component. And we could have a distributed message queue service for a web application. So imagine that a single web application consists of multiple components, each of which can drop messages into one or more different queues that can be then read by other application components, whether for the same application we're talking about or even a different one in a distributed internet model. So what we're saying then is that queues enable for the decoupling of application components, which means we're removing the real-time need for everything to be online at the same time to exchange messages between modular components. So this means also that delivery is guaranteed even if we've got intermittent network connectivity issues. It also means overall the service would be considered highly available and reliable. However, first in and first out, or FIFO, for messages placed into a queue is not guaranteed. So this can be useful sometimes if you have a particular application component that can produce data faster than another component can consume it. Some features of the Simple Queue service include, well, because it's running in the Amazon Web Services cloud, it means it's got a redundant infrastructure. It supports variable message sizes to be dropped into the queues. And this and other settings are configurable per message queue. A queue can have multiple readers and or writers. We can also set delay values in queues, like visibility timeouts for how long something remains in the queue that can be consumed by one component while being invisible to other components. We can even set access controls. So we might, for instance, grant access to a totally different AWS account to one of our message queues. And we would do that through what's called an Amazon SQS policy. Pictured on the screen, we have a diagram illustrating the Simple Queue Service message lifecycle. Now, starting on the left, we've got what's called a visibility timeout clock. We'll talk about that a bit further as we go through the lifecycle, because you can see in the diagram that that visibility timeout clock has changing values through each of the three phases listed here. But let's start with one thing at a time, the first phase of the SQS message lifecycle. So let's say our application, our web application, has a component, a modular component that performs some function for the app that we'll call component A. So based on the usage of the application, at some point, component A will send a message to a queue. And we're going to call that message message 1. Now, in the next phase of the life cycle, we've got a different application component that we're going to call component B. Now, component B will retrieve message 1 from the queue, if that's how it was programmed. And when that happens, that triggers the visibility timeout period to start. What does that mean? Well, with the visibility timeout, it means that message 1 will not be visible to other components reading the queue, other than component B, because it triggered it, until that timeout value has expired. So then, in the third phase of the life cycle, we're still working with component B, which processes message 1 and then deletes it from the queue during that visibility timeout period. So then it's removed. So we can see then that depending on the nature of our applications, we might have modular components that result in output that gets consumed by other components. And we don't want to have a real-time requirement for that to happen. And that's exactly what Amazon Web Services Simple Queue Services is all about. Here in the AWS Management Console, you'll see options related to queues way down, all the way down under the messaging category where you'll see Simple Queue Service. So if I click on Simple Queue Service, that's going to take me into the Management Console for that AWS service offering where we can begin to manage existing queues or even build new ones. Now, because we don't have any queues, we're put on the landing page where we've got a Get Started Now button, along with all of the documentation where we could easily learn more about SQS in this case. I'm going to click Get Started Now just so we get a sense of how we would do this. So I'm going to call this App 172 Q1. Now you would do this with knowledge of the modular application components that need to drop messages into a queue and also read them from the queue. So we could have a standard queue where FIFO, or first in, first out, is not guaranteed, or we could specifically specify a FIFO queue, again, depending on what we need. Do we need it to be such that items placed in or first in are always the first out? That may or may not make sense. So it depends on what we need. So if I were to choose configure queue, then I have a lot of the settings that we have alluded to. So the default visibility timeout, which is set here to 30 seconds, but I can change that to minutes or hours. How long to retain messages, the maximum message size. Again, these are settings that we configure per message queue. Also, we've got delivery delay settings. Now, if you're wondering what the difference between the visibility timeout and the delivery delay is, remember that the visibility timeout only is triggered when a consumer reads a message from the queue. With the delivery delay, let's say we specified 30 seconds for that as well, it means that when a message is dropped into the queue by an output component, we'll call it, nobody sees it for that delay period. So it's not triggered by being consumed, as is the case with the default visibility timeout. So depending on our needs, we'll determine what we configure these values as. So we've got a number of options that are available here, including enabling server-side encryption if we want to secure our data, maybe to be compliant with regulations for application component messages stored in these queues. And after that, I can click the Create Queue button, and now we see our application queue listed here, and down below we've got the tabs where we can go make changes, including adding permissions, or if we go to encryption, we can see that we've got options for server-side encryption. Currently, it is disabled. So we've got a number of things that we can do. At this point, to move further ahead with this, developers would programmatically write their code to put messages into the queue and to have other components read messages from the queue. In this exercise, you'll get started by differentiating reserved versus spot EC2 instances. Then you'll provide the syntax for creating a security group using the Amazon Web Services CLI. You'll also provide the syntax to create a security group, but this time using PowerShell. Finally, you will deploy a Linux virtual machine into the Amazon Web Services Cloud using the CLI. So go ahead and feel free to pause this video and try each of these 4 exercise steps out, and if you need help, come back to view the solutions. A reserved EC2 instance means that you are setting aside computing capacity ahead of time for between 1 to 3 years. And because you're setting that long-term commitment ahead of time, there is a discount compared to the standard on-demand EC2 instances. So we can use this then to guarantee not only that we get a discount, but that if we get a failed EC2 instance, that there is a replacement one that will take over. Now, spot instances are essentially additional unused AWS capacity. Now, it does provide the same performance as an on-demand EC2 instance, but instead of paying per hour at a given rate or ahead of time like with a reserved instance, what happens is you make a bid for low-priced instances, and if that bid is met, if it meets the appropriate pricing, then you get it. However, your instances, your spot instances could be interrupted if the going price for those spot instances exceed what your bid value was. So don't use spot instances when you need reliability. But if you're more interested in cost for things that aren't absolutely crucial, it might be a good choice. To create a security group using the CLI, we use the AWS EC2 create-security-group syntax. Now with the CLI, all parameters are always prefixed with a double dash, so dash dash. But in some cases, when you see it in print, the font may make it look like a single dash. It's not. So parameters are always prefixed with dash dash, such as group dash name, where I'm calling my security group here Windows Allowances. Dash dash description. I specify the description, and I have to specify the VPC ID, that I want to associate my security group with. And you can acquire that using command line tools or using the AWS Management Console. Now, a security group needs rules to determine what traffic should be allowed into or out of EC2 instances. We handle that in the CLI using AWS EC2 authorize-security-group ingress for inbound rules. So we would use the -- group ID where we specify our security group ID, and we would use -- protocol to specify the protocol, in this case TCP, -- port, in this case 3389, and then -- CIDR where we specify from which locations this inbound traffic should be allowed to be initiated from. Using PowerShell, we can build a new security group using the new -EC2 security group commandlet. I would then use the VPC ID parameter and specify that ID value. I would set the group name and the group description. Now, I then need to build a rule. So here, in my case, I'm building a variable called rule1, and I'm using new-object space amazon.ec2.model.ip permission. And I'm calling upon the IP protocol from port and to port properties using the dot notation and filling in the appropriate values for the rule. Then, finally, I use the IP ranges add method, so the .add method, and I'm adding from where this should be able to be initiated from. So I'm allowing inbound SSH traffic on port 22 from the specified IP CIDR range. Finally, I then use the grant-EC2 security group ingress commandlet to put it all together. So I'm giving it my group ID. Here I'm going to reference my variable that I started in the first line. And then, of course, I use -IP permissions. And I've only got one rule, but we could have more than one in a comma-separated list within the parentheses. So here I've just got $rule1 within parentheses and an @ symbol. The last thing we need to do is deploy a Linux EC2 instance using the CLI. So I would use AWS EC2 run-instances. I have to acquire the Amazon machine image from which I want to base my new Linux EC2 instance. So here I'm just taking the Amazon Linux AMI. I only want one instance. It's going to be T2 Micro. I'm using a Linux key pair that I've already pre-created, and I've specified the security group ID and the subnet ID that I want this to be related to. So I'm going to go ahead and press enter to build that Linux instance. So this output is good news. The next thing I'll do is use the AWS EC2 create-tags syntax. Now I need to specify the resource ID for the instance I've just created. So I'm going to paste that here in the placeholder in my command line. Once I've done that, I'll then use --tags where I'm going to set the name to a value of Linux 5. And I'll go ahead and press enter, and then we'll verify its existence in the EC2 Management Console. And we can see our Linux 5 virtual machine is currently running and in the midst of initializing.
gonna die. She's got corona. She's got corona. Này chỉ đâu khơi người ta chỉ cảm nhận khơi cả corona. Oh, you're so good. You let me sing, huh? You let me sing, girl. Khơi dầu. Khơi dầu corona. Corona. Nếu chỉ đâu khơi. Oke, muncul. Kara.
Hi, I'm Dan LaChance. Amazon Web Services provides numerous caching services and performance and high availability solutions. And in this course, we will explore those options. Caching speeds things up. Whether we're talking about caching CPU code at the firmware level, or whether we're talking about caching website content for users, it really does improve the user experience. So when we talk about caching in Amazon Web Services, we're really focused on where data is stored for the quickest possible access, whether that means putting things in certain locations geographically or reading data from memory rather than from disk. Memory is thousands of times quicker even than the fastest disk subsystem. So considerations would include, how often does the data change? Because if it changes often, we have to think about making sure the cache has the most up-to-date data. We should think about the type of data that's being cached, including the amount or size of it. Because if we're replicating across long distances, it will take longer if we have a larger data set that we need to replicate. And, of course, we should think about the location where data should be cached. If we've got the bulk of our users accessing a web application in Southeast Asia, then we should make sure the content is placed there rather than being hosted in Western Europe or North America. There are a couple of types of caching that we need to think about in Amazon Web Services. There's the AWS Storage Gateway. There's a Content Delivery Network or CDN solution in the form of AWS CloudFront. We've got the Elasticache in-memory database solution, and then there are some other database options that could speed things up by caching. So why don't we talk about each of these in further detail, starting with the AWS Storage Gateway and its volumes. With this solution, data is stored locally on premises through the use of a virtual machine. That's what the AWS Storage Gateway is. And we run that virtual machine on our equipment on premises. Now, we just need to make sure that we've got enough disk space on our hardware on premises for the entire data set that we want handled by the AWS Storage Gateway, because it will then back that data up asynchronously to the AWS cloud. The great thing about this is it provides clients with local access that would be on our on-premises networks to data sets with low latency, but at the same time, the data is being backed up off-site. So our volumes can be up to 16 terabytes in size with this solution, and the gateway supports 12 volumes, so in total we get 192 terabytes of potential storage space for our data sets. Now, this gets maintained in our on-premises data facility, and it's certainly useful for a disaster recovery or backup solution. With gateway stored volumes, after we install it on a host, the gateway stored volume can then be mapped in a couple of different ways using direct attached storage, otherwise called DAS, or a storage area network, otherwise called a SAN. So we then have the option of taking backups in an incremental fashion by taking what are called snapshots of the storage volumes. And that can either be done in real time or we can schedule it. Pictured in our diagram, we can see that we've got the gateway virtual machine in the center. It's listed as Gateway VM. And from there, down below it, it is accessing our storage equipment. This is all happening in our on-premises data center. This portion is not in the AWS cloud. Now, it's considered a caching solution because essentially we've got data cached locally on our on-premises environment so that it's accessible to clients quickly instead of having to go to get it through the cloud. However, the idea here and the link to the cloud is that our gateway stored volumes get replicated to the cloud and stored in Amazon S3, so we've got an off-site copy of data that's kept up to date. So clients have local quick access, we've got off-site storage for backups. It's all good for disaster recovery. A content delivery network, or CDN, in Amazon Web Services comes in the form of the CloudFront service. This caching solution is designed to put data near users geographically so that content gets served from a caching server near users rather than from an origin server. So if the origin server is in North America, but we've got a large audience in Southeast Asia, we're going to want to make sure that the content is served as close as possible to those users in Southeast Asia rather.
Raw pumpkin is not recommended. Yes, it's an amazing fruit.
Than retrieving all the content from North America. Another caching solution in Amazon Web Services is Elasticache. Essentially what we have here are in-memory data stores. So instead of retrieving everything from a database on disk, we can access it from the quicker memory. So it allows for quicker data retrieval, and we have a couple of options when we configure this. Now, these support open source solutions such as Redis and Memcached. Both of these are multi-node clusters that work together to make all of this possible, database caching, and it's scalable to large amounts of memory. Other options for database caching, of course, are possible indirectly through the use of Elasticache because that's primarily what it's really for. However, there's also another option called AWS DynamoDB Accelerator. So it's specific to the DynamoDB service offering. It's otherwise called DAX. And it's a solution that's designed to improve access time for content in a DynamoDB database up to 10 times. The great thing about this is we don't have to worry about the underlying infrastructure and the cluster setup to make this work. Instead, we can focus on the nature of the application, which serves business needs, and not the underlying technical details. So this is similar then in nature to Elasticache, because with DAX, we're really talking about an in-memory cache of data from tables in DynamoDB. And remember that DynamoDB is a NoSQL type of data store. Let's talk about database caching. In Amazon Web Services, database caching comes in the form of Elasticache, DynamoDB DAX, and database replication. Let's talk about each of these, starting with Elasticache. The Elasticache service offering is an in-memory caching solution. And we know that reading things from memory is far quicker than reading it directly from disk. So with Elasticache, frequently accessed items get cached. The great thing about Elasticache is if we already have an existing application, let's say we've got a multi-tiered app that's got a web front end and a database back end, it's pretty easy to add Elasticache to our existing application. There's minor configurations required between the front end and back end tiers to make sure that data is accessed through in-memory caching. We also have the option of adding and removing cluster nodes so it's scalable. The beauty is it's a managed service in the AWS cloud, so we don't have to worry about the technical expertise required to manage the cluster or to establish it initially. It's all handled for us by Amazon Web Services. Elasticache has two options that you'll see when you go to configure it. One is memcached, the other is Redis. These are both open source solutions that are used for in-memory caching to speed up performance, primarily for databases. They're both horizontally scalable, but memcached is designed to be very largely scalable, and it also is designed specifically for database caching. Redis is used to sort in-memory data sets. And when it comes to data persistence, we get that option available through taking snapshots. However, if we have data written between snapshots, then of course it wouldn't be persisted. DynamoDB Accelerator, otherwise called DAX, supports the DynamoDB NoSQL solution in terms of in-memory caching, similar to Elasticache. However, it's designed specifically for DynamoDB and provides a 10 times query performance improvement. So the purpose of this is to really speed up repeated read requests for content stored in DynamoDB tables for items. However, currently, only a Java SDK exists for accessing and managing DynamoDB Accelerator. Database replication is not directly an in-memory database caching solution. However, it does provide data redundancy. And so, depending on the database engine that we would select, let's say with Amazon Web Services RDS, would determine exactly what type of replication is used. It's based on the database engine that supports replication in and of itself. So whether we're talking about MySQL, MariaDB, or PostgreSQL. So the result is that we can have a multitude of read replicas. Now by doing this, we are improving read performance. And if we have a problem with our primary writable replica of a database instance, then we can promote read replicas to writable as needed. When it comes to Microsoft SQL Server and Oracle with Amazon Web Services RDS, we can configure these as multi-instance deployments where we can have what are called standby replicas in different availability zones. So that if we've got a problem within one availability zone, and remember, an availability zone doesn't necessarily map to a single physical Amazon Web Services data center. But if we have a problem in one, then we can rely on standby replicas and still have our data available. Another form of caching that we can take advantage of with Amazon Web Services is web caching. This often comes in the form of reverse proxying, geographic content caching, or the use of key value stores. Let's start with reverse proxying. Now, when we have a forward proxy, we're talking about internal clients making requests for internet content through the proxy. So the proxy takes that request on the internal client's behalf, goes out and gets it, and gives the content back to the internal user, while it can also cache it for subsequent requests. We're talking about the opposite, which means we don't have internal clients, we have external clients on the internet. So reverse proxying is also called web application acceleration, where HTTP requests are received from external clients, again, on the internet. So the HTTP requests then get cached on the reverse proxy host for future requests to speed things up. So if we've got a request for certain types of content from our back-end origin servers, it can be served up to clients asking for it in the future because it's been cached. So this is also considered a client-facing cache. If we take a look at the diagram, we can see we've got a client. This is a machine with a web browser, whether it's a PC, laptop, tablet, smartphone, doesn't matter. But we do have a client with a web browser requesting some kind of content from the internet. Now, they're coming in over the internet to our reverse proxy server host, whether that be a virtual machine or whether it be an appliance that we've acquired from the AWS marketplace. But either way, the reverse proxy server somehow has to be accessible from the internet and could even be behind an elastic load balancer. But anyway, the reverse proxy server then will take those HTTP requests and then get the content from the appropriate backend origin server. Now, the idea is then it will cache it for subsequent requests to speed up the serving of those requests. Then we've got geographic content caching, and that's essentially a content delivery network, a CDN. And in Amazon Web Services, that's called CloudFront. And it works with either static or dynamic content. In other words, rarely changing versus often changing content. And only the rendered pages actually get cached. So this deals with items such as web pages or images, video, that type of thing. When we place things close to users geographically, their experience improves because it's quicker to access that content instead of accessing it, for example, from an origin server in a different continent. Another type of caching is key value store caching. And this really deals with memory-based data stores. By putting a lot of key value pairs in memory, that means it is quicker to access it than it would be from reading it from disk. Now, in ElastiCache in Amazon Web Services, we can choose to use either the Memcached or Redis clustering solution. And they have the ability to cache pretty much any type of web content, so not just HTTP responses. It also allows us to have a private network cache not directly accessible by clients. So where a reverse proxy caching server then would be designed to be public-facing on the internet, the key value in memory-based caching solutions are often used internally with the database tier, which is not directly accessible by external clients. Whether we're talking about using ElastiCache with Memcached or Redis, which you get as an option when you configure ElastiCache, either way, it's a set of cluster nodes that work together to make this caching possible, to have all of this available memory space in RAM to cache key value pairs. So it works well with heavy read workloads. That's really what it's designed for. So any type of heavy requirement on a service or an application related to social networking perhaps, or gaming, or media sharing, or maybe even database querying on a large scale with very large data sets, such as with big data analytics. Pictured in our diagram, we can see at the bottom that we've got something labeled as a distributed cache. So this way, with some high availability built in across different availability zones, here AZ1 on the left, availability zone 1, on the right, AZ2, availability zone 2, what we could do is we can mirror our reverse proxy or web accelerator, if you want to call it that, solution. And of course, we could have web servers in each availability zone. And when we talk about using cached web content through Amazon CloudFront, which pulls its content from S3 buckets, that's also something that could also, of course, be cached with a reverse proxy web server. So some of these solutions can work together to provide the optimum user experience. But we might want to make sure that we've got some redundancy built in by essentially mirroring our solutions across availability zones. One great benefit related to cloud computing is how quickly scalable it is. Think about traditional on-premises scaling, where you need to determine what your needs are for things like equipment, that's hardware, and software and licenses. Then you have to order that stuff, you have to wait for it to be shipped or downloaded. Then the IT team needs to configure that equipment and software. Then it needs to be maintained over time, which means tweaking those items for performance, upgrading them, and patching them. So it's an investment not only in the equipment, software, and licenses, but also in the time to set it up, configure it, and to maintain it. Now, if we think about cloud scalability, the term that comes to mind is rapid elasticity. We don't have to worry about acquiring the underlying infrastructure to support our computing needs. It's available at the click of a button with Amazon Web Services, hence rapid elasticity. So it allows for the dynamic adjustment of cloud resources to meet our specific IT computing needs, whether it be requiring more or even less storage space, or maybe dealing with a number of EC2 instances, whether we're adding or removing them to meet the demand for an application. So whether those instances are behind load balancers, ELB or elastic load balancing in Amazon Web Services, or maybe we are adding EC2 instances in the form of cluster nodes for Elasticache for in-memory cached data sets, or maybe we're changing the number of EC2 instances supported by Elastic Beanstalk. Now, Beanstalk is a service that helps us deploy groups of items together, like EC2 instances, S3 storage, and so on. Horizontal scaling is an important part of talking about the cloud's ability to provide us resources rapidly. Horizontal scaling means we are adding or removing virtual machines. Now, either we scale out by adding more virtual machines, which can support, for example, Elasticache requirements. So by adding cluster nodes, we are scaling horizontally, or we can also scale in to reduce the amount of virtual machines that support a given solution. Now, we would do that because there's no sense paying hourly charges for EC2 instances if they're not needed. Vertical scaling means that we're adding more underlying horsepower to the existing virtual machines. So remember, horizontal scaling, you're adding or removing virtual machines. Vertical, you're really just changing the underlying power of what you've got. So we can change our instance types, maybe, for example, from T2.micro to M3.large, depending on the amount of virtual CPUs and the amount of RAM that is required for a specific solution. But again, we can scale up to add more horsepower or scale down to remove it as required. You're always going to be interested in scaling down when you don't need as much horsepower, because then you're paying less in terms of an hourly charge for your EC2 instances. We also have to think about our service level agreements, or SLAs, because in Amazon Web Services, there's an SLA for each type of AWS service offering. The reason we should consider the SLAs is we have to take a look at the details related to charges, whether we are scaling up or out or in or down. We're adding and removing service capacity. So what are we going to be charged? And of course, always remember to shut down or delete unused resources depending on your needs. Things like EC2 virtual machines and especially RDS database instances. Because depending on your configuration, it doesn't take long to keep RDS database instances running when you're not using them and to build up a very large bill. So be very careful with that. We can also use EC2 spot instances. Now, spot instances provide a reduced cost for existing unused AWS capacity. So essentially, we put in a bid, and then we will get the option to use EC2 spot instances. But that comes at the possibility of knowing that spot instances could be interrupted at any time. So it's not a good choice for mission-critical solutions in the AWS cloud. However, it is a good choice for non-essential testing. So when it comes to fees that we are being charged for these services, remember, it always depends on whether we're scaling up or down, so changing instance types, for example, or whether we're scaling in or out, so whether we're removing the number of EC2 instances to support a solution or adding them. In this video, I'll talk about horizontal scaling. Now, why would you be interested in horizontal scaling? Well, one of the great things about the cloud is that we can add and remove resources as needed, especially in response to demand for a busy website, for instance. So horizontal scaling is also called scaling out or scaling in. Scaling out means that we are adding EC2 instances to support a solution. whereas scaling in means we are removing EC2 instances that aren't required any longer. Now, it's important to always scale in when you aren't using something, because otherwise you are still paying, in the case of EC2 instances, you're paying the hourly charge for virtual machines that are left running, even if they're not being used at all. So when we talk about horizontal scaling, we're talking about improving the workload capacity. That comes in a couple of different forms. Consider, for example, using databases, such as RDS read replicas for read-intensive apps. So we can spread out that workload across multiple database instances instead of having it all happen on a single one and overloading it and ultimately reducing performance. Another example would be adding EC2 instances through auto-scaling, perhaps in response to CPU utilization for a web app. Pictured on the screen, we've got a diagram related to database or RDS horizontal scaling in the AWS cloud, where on the upper left, we've got an elastic load balancer. Now, it is serving up content from, on the bottom left, our RDS DB instance. We're going to call that the source or master DB instance because it allows not only reading, it allows writing in terms of deletes, updates, or inserts to the database. However, then pictured on the right, we have 3 separate and independent DB instance read replicas. Now, read replicas can be created in different availability zones or even in different AWS regions so that we've got true disaster recovery as an option. However, depending on what your purpose is, whether it be disaster recovery or performance, you might not want to split your read replicas that far apart across regions. So again, as usual, depends on the need. Now, if we have a failure in our source database instance, the one that's writable, pictured in the bottom left in our diagram, then we have the option of promoting a read replica so that it becomes writable. We also need to consider, with horizontal scaling, the specific operating system and even apps running within the instance. For example, depending on what we're doing, maybe using the Linux operating system within an EC2 instance is better suited if we're doing something like HPC or high performance computing type of work. So really, we have to think about the workloads running on top of these EC2 instances to make decisions based on like the operating system and also the instance type, the horsepower of each individual underlying virtual machine. Now, when you're changing that, you are scaling up or down. That's vertical. We're really talking about horizontal scaling, but yet the two are intertwined and both must be considered in a solution. We've also got another great AWS option called placement groups, where EC2 instances can be grouped together within the same availability zone, which is designed, of course, to reduce network latency. So we've got a diagram here where we've got a logical group of instances within the same availability zone, which allows us to use the low latency 10 gigabit per second network provided by Amazon Web Services. So sometimes when you scale horizontally, you still also need the performance, in which case you don't want to spread out your instances, for example, across different availability zones or regions. So again, we really have to look at what our requirements are in terms of servicing our horizontal scaling to support a business process. The IT workloads running within your EC2 instances will determine whether or not you need to scale vertically. Vertical scaling means that we are either scaling up or scaling down. So when we add more underlying horsepower to a virtual machine, we are scaling up. So for example, when we talk about virtual or vCPUs that we can configure based on the instance type, it really equates to a single CPU thread when we talk about the physical underlying hardware in the hypervisor. However, this will vary based on the specific instance type that we select. We might also consider the use of SSD or solid-state drive storage, essentially no moving parts, which increases the IOPS. So if we think that performance is suffering through our workload because of disk read and write access. We are changing perhaps our instance storage, such as using we are increasing our network performance, so increasing bandwidth, and maybe we are adding IPv6 support. Now, all of these factors get bundled together within the instance type, and depending on the instance type we select will determine our hourly charge when that instance is running. So we might go, for example, to M4.10x large or P2.16x views it needs and how much RAM and so on. So we can change the instance type even for an existing EC2 virtual machine. However, that doesn't change. That's especially good to know if you've got AWS CLI or PowerShell scripts that refer to that instance ID. But the thing is, when you change the instance type, as we see pictured on the screen here, in this case for running within your EC2 instances, is licensed based on the number of CPU sockets or cores. This is often the case with database software. However, we have to think about storage, because just because we're changing our instance type, for example, to scale up, it doesn't mean our storage is changing, the actual data on the storage volumes. When we do make a change to the instance type, it can happen pretty much immediately. Rapid elasticity is one of the things that makes cloud computing so compelling. That's also true with Amazon Web Services auto-scaling. Auto-scaling is used to adjust the number of underlying EC2 instances that support some kind of a service up or down. So the idea is that we can ensure proper application performance so that when there are peak demands, we have more underlying virtual machines handling that load, and when the demand dies down, we can then
work it out.
Này, cái tụi mình quát rau nè. Vậy chỉ xíu hơi phí phí lại thà.
Okay. 就係 2 minutes ago 就係 PP 啊。
Ồ,已經 PP 咗啦。
Yeah. 好啦。
自己翻嚟？
Yeah.
哇 ，so danger！ 我話你聽地，佢走咗，你開唔切個門，你追唔到佢啊。
No, but yeah. Gee.
因為我覺得落咗啲 hair 仲係好 dry 嘅。慢食，慢食啲。哎呦，你踩死我啦！唔好踩我，唔好踩我。
Molly, you're so heavy now. Oh God, my 7, 8. Ow!
This is done in AWS by building what's called an auto-scaling group, which is just a collection of EC2 instances where we specify the minimum number of instances, as we see in the screenshot. We can also see the maximum number of instances that we can horizontally scale out to. Pictured in the diagram, we can see that with an auto-scaling group, we configure the minimum size, that's the number of instances it will always have as a minimum. We can set a desired capacity and an absolute maximum size. There are different things that could trigger the auto-scaling options to add or remove EC2 instances. Things like exceeded CPU utilization over a period of time. That might indicate that we have a very busy application and that we need to scale out horizontally. At the same time, we'll have a schedule for auto-scaling. So when you work with where we specify things like the AMI, the Amazon Machine Imager template that we're going to use to build our EC2 instance, things like the key pair that would be used so we can authenticate the number of vCPUs, the amount of RAM, and so on. Whether or not we want to use spot instances by adding EC2 instances